Okay, so it's my pleasure to introduce our second speaker, second lecture for today, from Mesland, from the University of Leiden. And his title is, well, Group C algebras and K-theory. From?
Well, the title would be, that's the title of the series. Today's title will be something like Group C-star algebras and cross products. So, for the first part of this, I will actually try to connect regularly to some of the things Peter said this morning. I will talk a bit about C-star algebras, so what they are and some fundamental results. And then I will associate to a locally compact group G, two objects called the full and reduced C-star algebras, which depend on the topology of the group and some other things. And the C-star algebra of G, this is sometimes called the full C-star algebra, the first one, that's related to the unitary dual of G, whereas this reduced C-star algebra is related to the tempered dual. And we will see that the representation theory of G can maybe in some sense be understood in terms of these algebras. Now, for those who are a bit more algebra minded, so if G is discrete, then both C star G and C star reduced G are completions of the complex group ring of G. That's just if you've seen that object, like if you have a discrete group, you can build a ring out of it. And these analytic objects that I'm going to define will contain this group ring densely. If G is not discrete, then this is not the case. So then this is really a different type of object. But okay, to get into this discussion, we have to talk about C-star algebras and what they are. So you can define these in different ways. There are two definitions that one could use and that are actually equivalent through a famous theorem. So the first is that C-star algebra is a closed star subalgebra of the bounded operators on some Hilbert space. So H denotes a Hilbert space. And the second one is that C-star algebra is a Banach star algebra such that, so this means it's a Banach algebra with involution such that the norm and the involution are related by this identity, meaning the norm of x star x is exactly equal to the norm of x squared. In general, you would have that the norm of x star x is dominated by the norm of x squared, and the equality is something that does not come for free. B of H, the algebra of bounded operators on a Hilbert space, maybe I want to actually not call this X, but to call it A. The algebra of bounded operators in a Hilbert space, this identity is satisfied, but it's special because it ties the norm to the spectrum. So this C-star identity ties the norm to the spectrum. If you are not familiar with the notion of spectrum that I'm talking about, then that's not a problem at the moment. But this identity is very special and was long sought for to be the right thing to describe these algebras, because there is a theorem that now tells you that these two definitions are equivalent. So let A be an abstract C-star algebra. So that means that it satisfies definition number 2. Then there exists an injective so-called star homomorphism pi from A to B of H for some Hilbert space H. So this means that given a Banach star algebra satisfying that C-star identity, you can actually construct Hilbert space H such that this algebra is realized as an algebra of operators on that Hilbert space. So star homomorphism means algebra homomorphism that also intertwines the stars. So the abstract star in A is intertwined with the concrete operator adjoint in B of H. All right. Now there is a second theorem, because here we're just working with abstract complex algebras, and they need not be commutative. And the examples we're interested in, these group algebras, won't be commutative, but for motivation, a lot of other things we're going to see, we want to also characterize the commutative algebras. So if X is a locally compact Hausdorff space, then C0 of X, which I define to be the space of continuous functions, so F is continuous, and vanishes at infinity. Now this notion of vanishing at infinity, well, especially the first time you see it, you need to define it carefully, but it means that these functions, f, if x is not compact, become as small as you like outside of compact subsets. So f vanishes at infinity if for every epsilon greater than 0, there exists some compact subset such that outside of this compact subset, f is smaller than epsilon in absolute value. So this C0 of X is an abstract C-star algebra, is a C-star algebra in the norm it's called the soup norm in functional analysis, and the involution f star of X is by definition the complex conjugate of the value. Okay, you can check this is a C-star algebra, and now the next remarkable result is that this is called the Gell-von-Neumark theorem, and it says the following: let A be a commutative C-star algebra. And now it doesn't matter which model I use. I could use the abstract model or the Hilbert space model. Then there exists a locally compact Hausdorff space X such that A is isomorphic to C0 of X and now as C star algebras. So this means that there is a map between the two that intertwines all the structure. So multiplication and the star structure. And so this tells you that commutative C star algebras are dual to locally compact Hausdorff spaces, and that's where we make contact with representation theory, because as with groups, we can also think of representations of C star algebra. So C star algebras. So a representation of a C star algebra A is, by definition, a star homomorphism pi from A to B of H pi. So a representation could be denoted by pi, comma H pi, where H pi is a Hilbert space. And you can say that such a representation is irreducible if the only pi A invariant subspaces of H are 0 and H itself. Okay, and this gives us the notion of what's called in C star algebra theory the primitive ideal spectrum. Let's first observe that by the Gelfand-Naimang-Searle representation theorem, we know that any C star algebra has a faithful representation, meaning an injective representation on some Hilbert space. But there could be more. So now we define the primitive ideal space of A as the space of those ideals. So J is an ideal. Well, I don't have to say that maybe. J is equal to the kernel of pi with pi some irreducible representation. This is called the primitive ideal spectrum, and this can be made into a topological space. So there's a topology which I will very roughly describe. It's called the whole kernel topology. And it says the closure of some set of primitive ideals is the set of primitive ideals for which the intersection of all the elements in a given set is contained in that primitive ideal. Now, this is a well-known topology, and the GNS theorem, the Gelfand-Naimang theorem, sorry, about commutative C star algebras. So if A is commutative, then A is actually isomorphic to the continuous functions on this primitive ideal space, because the irreducible representations will be all one-dimensional. And then you get maximal ideals, which are points, and you're playing a game that's very similar to algebraic geometry. In general, this space prim A is bad. It's not Hausdorff in general, for example, as was mentioned in the discussion preceding this lecture. And so you cannot expect any general theorem like this. Of course, when your algebra is non-commutative, C0 will always be commutative. So there's no hope to expect anything like that, or to even recover your non-commutative algebra from this primitive ideal spectrum is not the way to go. So what the philosophy of non-commutative topology and non-commutative geometry is that so NCG A is the space of functions is the algebra of functions on some non-existent topological space. So we have a topological space associated to the algebra, but that's definitely not how we think of the algebra. But this is the philosophy. Okay, now let's go to group actions on C-star algebras. So group actions on C-star algebras. So we have a locally compact group and that's all along, and to a C-star algebra A we can associate this group here, odd A, which is phi from A to A, and phi should be a star isomorphism. This is clearly a group on the composition, and we now define the following, namely a strongly continuous action of G on A is a group homomorphism from G, I will denote it by alpha, from G to odd of A, such that for all A in A, the map, following map from G to A that maps G to alpha G of A is continuous for the norm topology. For the norm topology on A. This is the kinds of actions on C-star algebras that we want to restrict ourselves to. And of course, again, the example from commutative land that you need to keep in mind is that if G acts on X by homeomorphisms, then alpha G F of X defined by being F of G inverse acting on this X. That's a strongly continuous action of G on C0 of X. All right. Some further remarks on GC-star algebra. So if A carries such a strongly continuous action, then we call it a GC-star algebra. Now, an object that we will encounter is the fixed point subalgebra. So I will do my best to instantiate the action, because sometimes we will use two different actions on the same C-star algebra, and then they're not the same as the G-C-star algebras. I may sometimes forget. So I will write A alpha to be a G-C-star algebra, alpha indicating the action. Then AG, which is those A in A, such that for all G in G, alpha GA is A, is a C-star subalgebra. So this sits in A. And we call it the fixed point algebra. Now, if G is compact, then we can do the following. Then we can define a map rho from A to AG by just integrating over the action with respect to some R measure. We want then the group to have full measure 1, otherwise you need to normalize by that. But this gives me a map onto the fixed point algebra. So this is, so it satisfies that rho A star A is positive, and for all B in AG, we have that rho AB is rho A times B and rho BA B times rho E. Such maps are called conditional expectations onto some subalgebra. But this, of course, uses the compactness of G in a serious way. This thing in general doesn't exist, so in general, AG can be 0. And that's especially when you're working with non-unital algebras. So the simplest example here is take the action of R on itself by translation. So just additive translation. Then this gives us an action of R on C0 of R. So the one R is a group, the other R is just a space. And you can easily check that the fixed points for this action is 0. That's because a function, if a function were fixed, it would have to be constant, and the only constant function in C0 of R is the 0 function. So this is both the non-compactness of the group and the non-compactness of the space that you act on that causes this. And it's just good to keep in mind, because most algebras we're going to be interested in this week are not going to have a unit. So yeah, one needs to be aware of this. Okay. Peter already defined the strongly continuous actions on Hilbert spaces, so I'm not going to repeat that definition. But I'm going to define a covariant representation. So we say let A alpha be a GC star algebra and then a covariant representation triple pi h u, where pi from A to B of h is a star representation. U from G to the unitary group of H is a strongly continuous G representation. So that's very similar to the, so Peter gave this definition. I gave a version for C-star algebras. We're using both now. And the requirement is then that if I take the unitary operator associated to G and I conjugate it by pi G, then what we should find is the pi of the acted upon element in the algebra itself. So this relates the representation of G on H to the given action on A. And that's what we call a covariant Hilbert space representation. I want to generalize this to Hilbert C-star modules now. So first introduce this notion. And Hilbert C-star modules are in operator algebra theory are quite fundamental objects, which is why I think it's useful to briefly discuss them here. And they really, they unify several notions. So philosophically or morally speaking, a Hilbert C-star module is a Hilbert space, but not over the complex numbers, but over some C-star algebra. That said, one should also be careful with that analogy, because many theorems that hold in Hilbert spaces do not hold for Hilbert modules, but I won't elaborate on that too much. So let B be a C-star algebra, then a Hilbert C-star module over B is a right B module. E, so E is some complex vector space that carries a right action of E, which is an algebraic module. And it should be equipped with a, I should say, sesquilinear pairing written with these brackets. And it goes from E times E to B. Such that, well, and then there are some axioms which I will give, but they're really the same as those for Hilbert space inner product. So if I take the inner product of E1 and E2 times B using the right module structure, then I should get this. If I use the star in B, then that should be the same as switching the entries. These are really the complex inner product axioms. Then if I take in the product of an element E with itself, I should get a positive element of the C-star algebra. Now, I didn't introduce or discuss positivity for C-star algebras because of time constraints, but there is a notion of positivity in C-star algebras, which for commutative algebras corresponds to functions that take positive values. And it's a very useful notion that gives C-star algebra some extra structure. So this exists non-commutatively. In Hilbert space theory, there is a notion of positive operator that coincides exactly with the notion of positivity in C-star algebras if you would view them as concrete C-star algebras, so Hilbert space operator algebras. And so this is positivity in B, so recall, so this I will emphasize. So this is not a positivity of a number because this inner product is not a number. So that's important here. And E is 0 should imply E is 0. So this is the non-degeneracy condition. And then there is the fourth. E is a Banach space in the norm defined by, okay, norm of E squared. We're going to set equal to the inner product of E with itself and then take its norm in B. There's some minor amount of work to check that this actually defines a norm, but it always does define a norm. And then the requirement is that E is complete in this norm. You can often construct Hilbert C-star modules by identifying such an inner product on some abstract module, and then once you have it, you can take the norm and take the completion of the object you have that is stable under the further properties, and that's how you can make Hilbert C-star modules. I will indicate this in some examples that are relevant to us. But the moral of the story is a C-star module is like a Hilbert space, very much like a Hilbert space, but the base is a C-star algebra itself. And the inner product takes values there. Yeah. Now, of course, the first example is if I have a locally compact space and I have a vector bundle with a Riemannian metric then the space of sections of this vector bundle carries an inner product, so let's call the Riemannian metric G carries an inner product. So if I take two sections, S1 and S2, I want to construct from that a function. What you do is you take the Riemannian metric at X and you take the inner product of the sections. At X, of course, this needs to be extended to well, it's a complex vector bundle, let's say that, from the start. Now, this is really the key example, and this is what Hilbert modules generalize. Of course, there's no finite dimensionality in the definition of a Hilbert C-star module. So, as an example or remark, so Hilbert C-star modules over C0 of X for some space correspond to, well, sections of, but so-called continuous fields of Hilbert spaces. So if you're given a Hilbert C-star module over some commutative algebra, then there is a bundle of Hilbert spaces over that space X, such that your module occurs exactly as the space of sections. here, continuous fields of Hilbert spaces are not necessarily locally trivial. So finite dimensional vector bundles are in here, but there's more in here. And fields of Hilbert spaces can have strange jumps and all kinds of things. It's all encoded in these axioms. And so, yes, if you take this point of view, there are, of course, definitions of continuous fields of Hilbert spaces that focus more on the geometric picture. But really what it is these axioms capture this notion.
Ron, there's a question. How
Yeah.
is it related to the Serres-1 theorem?
The question is, how is this related to the Serres-1 theorem? Well, yes, the Serres-1 theorem, at least in the first example, you use this because, well, there's a whole, so Hilbert C-star modules, so you can say many things about them. So if I have a Hilbert C-star module that is over a unital algebra that is finitely generated, then it's automatically projective. So if I have a compact space and I have a finitely generated Hilbert module, then I know it's projective. Then the Serres-1 theorem tells me that there is a vector bundle of which this is the sections. And then you get to the first example that I discuss here. So there is here over unital algebras, finitely generated and projective is the same as being finitely generated and Hilbert C-star, meaning that there is an inner product. Because on a vector bundle, you can always choose a Riemannian metric, and that's also how you prove Serres-1. I hope this covers the question somewhat.
Thank you.
All right. Yes, so some further stuff about Hilbert modules, operators. On Hilbert C-star modules. So if I have E and F are Hilbert B modules, then the space of adjointable operators is the space of operators for which there exists an adjoint, and this means that TEF is E T star F. No. And of course, one inner product is in F, the other one is in E. This is the space of adjointable operators. So it's operators that admit an adjoint, and such T, so only requiring the adjoint to exist is automatically bilinear and bounded for the norm. So we only need to require this algebraic condition of the adjoint to exist everywhere, and then we get all kinds of other properties we would like for free. The converse of this is false, so there are bilinear operators that are bounded, but that do not admit an adjoint. Again, giving an example would be would take a bit too long, but they're not hard to give. So yeah, the converse is false, but again, requiring the existence of the adjoint solves all your problems. Then we defined n star of BE to be just hom star of E to itself, and this is a C-star algebra in the operator norm. So that's nice. And the operator norm is just defined as you're used to. And this algebra has a specific ideal. So let's first look at finite rank operators. On E. So we take E1, E2 in E, and we form, I'm going to use the cat-bra notation. So we can make from two vectors an operator by just using the inner product. So we have two vectors, we take inner product with the first one and then multiply that from the right with the second one. So we use the inner product and the module structure to define this operator. In a Hilbert space, this would be a standard rank 1 operator. Now, we can take the C-star algebra spanned by these elements by definition, and this is a subspace of the adjointables that needs the following quick check. I mean, you can check that these rank 1 operators, the adjoint is just a flip. So you flip the cat and the bra. So that means that these rank 1 operators are adjointable, and then I take the C-star algebra generated by those things in the adjointable operators. Then the main result is that K of E is a closed two-sided ideal. All right, so this will come back in several forms. We'll use a bit of it in this lecture, but in the next couple of lectures when we discuss Morita equivalence, this will all be at our disposal. Okay, so now we can generalize the notion of a covariant representation on a Hilbert module. So covariant representation on Hilbert modules. And here it's important that let A alpha be a G C-star algebra and B a C-star algebra. And now it's important that trivial G action. So we will look at C-star algebras with a G action later as well, but then a covariant representation of A alpha is a triple pi E U, where pi from A to n star B is a star homomorphism. Should have probably switched page first. And U from G to now the unitary group of E. So E, like a Hilbert space, admits unitary operators. And you can use the same notion of strongly continuous representation, namely taking an element of E and then using that the map G maps to UG of E is continuous. So G goes to UG of E is continuous for all E in E. It's the same definition. Okay, and now I have to state the most important property on the next page, unfortunately. But it's the same as in the Hilbert space case. So as such that if we take UG pi of A, UG star, then that's pi alpha G of A. Okay, so that notion just generalizes. I want to make one other remark. If G is a strongly continuous representation, and this is the same in Hilbert spaces, then n star of E need not be a GC star algebra. So the strong continuity in the C star algebra sense may fail on the whole endomorphism algebra. For example, this already fails on a Hilbert space. However, K of E is always a GC star algebra. So that's another important thing to keep in mind. And this, again, already holds in Hilbert spaces. All right. Now let's go to the definition of cross products. Cross products. And we derive the group C star algebra as a special case of that. So we're going to look at the space. So A is a GC star algebra. And we're going to look at the space of compactly supported functions on G sub F is compact. Of course, F is continuous as well. So A is a GC star algebra. We have this space. This space carries a star algebra structure. As follows. So there is a convolution product. If I take two functions, I evaluate them on an element H, then I take the integral over G, F1 of G, alpha G, F2 of G inverse H. So note that the functions take values in the GC star algebra, so I can act on the values. You can check that this is an associative product, and there is a star structure also involving the action and the adjoint in the GC star algebra. All right, so now with this notion of covariant system and this notion of the convolution algebra, we can construct various completions. So following easy proposition is let A alpha be a GC star algebra and pi, I'm going to write EB now, and U a covariant representation on some Hilbert module, which could be a Hilbert space, then pi cross U will be a map from CCGA into N star of VE, and this is defined on a function f. So pi cross U of f should act on an element E, and this by definition will be given by this formula. You can check that this is a star representation. Star representation of CCGA. And so suppose this were injective, then if this were injective, you would get a C star norm from the endomorphisms on the module, and you could close it. You would get some C star algebra that you've constructed from G and A. All right, and now we can use this definition, this proposition. So we defined a full C star norm on CCGH to be
Ron, can I ask you a silly question? Do you need A equal to B or something?
No.
So
we're requiring B to have a trivial action. So and B will, I mean, for all it's worth right now, you could just think of B equal to the complex numbers.
okay, so f of g is an A, and how is that hitting on E as a module?
Maybe I should, did I oppress the pi? So yeah, there should be a pi here.
Pi of that, okay.
That's a good point. That was certainly what was meant here, yes. So use the whole covariant representation, thanks. So pi EU is a covariant representation. Now, if you've seen this definition before, then it often only uses the Hilbert spaces, as I said, but when you have a Hilbert module, you can represent the coefficient algebra, you get a representation on the Hilbert space, which is then isometric, so this doesn't change the norm. So I'm being quite general here, but as said, we can think of Hilbert spaces at this point only. The main reason right now that I'm working with the Hilbert module picture is because I want to now introduce the reduced cross product. So this is the full norm. It turns out to be a C star norm, and so the completion CCGA in this full norm is denoted.
There's a comment in the full. You take sup remum over the norm.
Yeah. Thanks. Glad people are paying attention. This is denoted A cross G and called the full cross product. And if A is equal to C with trivial action, then we write C star G, which in this definition would be C cross product, full cross product with G. Okay, I'm going to take the liberty to maybe go 5 minutes over time, just because then I can say everything I want. So this is the full cross product, and an observation is that is that unitary representations. Wait, no, I should say this. Irreducible star representations of C star G are in 1-1 correspondence with irreducible unitary representations of G. And I'm talking about Hilbert spaces now. And another way of saying this is that the primitive ideal spectrum of C star G, at least as a set, is equal to G hat. And because I defined for you topology on the primitive ideal spectrum, we now get a topology on G hat. This, as we discussed with Peter in the break, you can describe this topology purely representation theoretically. I now went a long way to first get an algebra, which is rather big also, because the norm is some universal norm that we didn't even address was finite, but it is. But this is one way to describe the topology on G hat. So that's what we have now. And now we go to the reduced cross product. And then by specializing to the case that A is equal to C, we get the reduced C-star algebra. But let's first discuss this reduced cross product, because you construct the reduced cross product by singling out a specific representation. So again, let A alpha be a GC star algebra consider the following: L2 of G comma A, which are, I should call them phi, functions phi from G to A, such that the integral phi A star phi A, no A, it's not so good, G, this integral is finite. Notice that I'm not, so this is again one of these C-star algebra Hilbert module things. Notice here we're not taking a norm. We're taking the positive C star algebra valued inner product that is the natural inner product on this object. So we're not taking a norm, we're taking the integral of positive elements in a C star algebra. And you can check that the functions for which this integral converges in norm, square norm, is a subset of this space, because this integral is dominated by the integral where the norm is inside, but this space is bigger. There's more stuff in here. And that's the usual thing you have to take care of when you work with Hilbert modules. So L2GA is a Hilbert module. Hilbert C star module over A in the inner product phi psi. Well, that's then the usual. And you can play your usual Cauchy-Schwarz games with slightly more subtlety to show that if this integral converges, then actually these cross-term type integrals also converge. So that then follows, and this L2 G of A becomes a Hilbert C star module over A. Now L2 GA carries a covariant A alpha representation. So the other important part here is that I am considering, when I look at A as the coefficients from the right on this C star module L2 G of A, I am viewing it as a trivial G algebra. I'm forgetting the G action when A acts from the right. I'm not forgetting it when it acts on the left. So if you look at my definition for covariant representation, you see that there was a trivial action required on the coefficient algebra. Yeah, in the next lecture, so I didn't discuss GC star modules because we don't need them right now, but they will come by as well. And there are other subtleties, but we don't need that here. But I want to emphasize that I'm considering from the right A with a trivial G action. Now the covariant representation is given by, so that's pi L2GA A U, and UG phi of H is defined to be phi HG, and pi of A phi evaluated in H is alpha H of A phi of H. Now you can check that these satisfy the definition of a covariant representation. So this gives us pi cross U from CCG of A into the adjointable endomorphisms. So here we have A acting from the left and from the right in different ways. And the definition is now that the reduced norm on CCGA is for pi L2GA U. So for this specific representation, I'm taking the reduced norm, and then if A is C, then L2GA is just L2G. And we are looking at the left regular representation. So in some sense, you could call this representation that I just defined the left regular representation of a G-C-star algebra on this Hilbert module. And we say that the reduced cross product a reduced G by definition is the closure of CCGA in this reduced norm, and C star reduced G is by definition the reduced cross product of G with C. And then as a last statement, because I'm really over time, it turns out that the space of tempered representations coincides as a set, at least, with the primitive ideal spectrum of this reduced C-star algebra, and so we also get a topology on the tempered dual, and we get an inclusion of closed sets, if I'm not mistaken. So tempered dual is closed in the unitary dual. This is related to, so there is a quotient map from the full C-star algebra to the reduced C-star algebra, extending the identity. And this also works on cross products. Maybe I'll say a little more about that tomorrow, because I think this is an important point. And that gets you this inclusion and also the closeness statement. And so there is, even though these are completions of the same dense object, you see that there is an ideal here floating around that is not visible on the level of compactly supported functions. But when you take these completions, you introduce an extra non-trivial ideal that is related to the tempered dual not being equal to the reduced dual. I apologize for going over time once more, and I will leave it to this for today.
Thank you, Bram.